Hello, and welcome to the video accompaniment to Chapter 2, Sections 3 and 4 of our text. This is the third video in the Chapter 2 series. In this one, we'll be talking about Cartesian products and partitions. If you haven't done so already, make sure you read through these sections in the book, familiarize yourself with the definitions involved. After reading through the text and watching this video, you should be able to describe the elements of a Cartesian product of sets, and list the elements of one. You should understand the definition of a partition, and you should be able to give a partition of a set. Let's get started. Oh, activity alert. Yeah, along with this one, I do have an activity, a set of activity problems dealing with Cartesian products of sets, and I'll point that out when we get to it. In order to first understand what a Cartesian product is, we need to understand these terms, ordered pairs and ordered n-tuples. Now, these things are actually, you should be somewhat familiar with these already, but perhaps not with this language. With ordered pairs, you're probably familiar with working with the Cartesian plane. Cartesian plane. So whenever you graph a function, graphs of functions, whenever you graph a function or plot points in the Cartesian plane, you're actually working with ordered pairs of real numbers. So here I'll draw a little Cartesian plane for us. So that's real numbers along this axis and real numbers along this axis. Usually call the horizontal one the x-axis and the vertical one the y-axis. And then every point inside of the plane, let me draw a few hash marks here. Every point inside of the plane is associated with it in ordered pair. So for example, this point, if this is 1, 2, 3, 1, 2, 3. So for example, the point 1, 3 is right here. So that would be the point 1, 3, which is an ordered pair of real numbers. Notice the difference here between sets. So it's kind of like a set containing two elements, except there's an inherent ordered structure to it. So notice that point 1, 3 is different from the point, every time I do that it messes up, is the point 3, 1. So these 2 points are distinct from each other, right? I mean, they're in different locations of the plane, and they're not considered equal to each other. On the other hand, if we have the set 1, 3, so with braces around it, that means set, that means unordered, that's the same thing as the set 3, 1. With sets, we don't care about order. It's the same no matter what order you write it in. With ordered pairs, we care about order. The point 1, 3 is not the same as the point 3, 1. Now, we don't only want to do this for the real numbers. So here we looked at the Cartesian plane. You're familiar with that and the ordered pairs there. But just given a set A, given two sets A and B, we can form the Cartesian product of them, and the elements of that Cartesian product form A cross B, and the elements of that Cartesian product are the ordered pairs where the first element is in A and the second element is in B. So we'll take a look at an example of this in a second, and hopefully that'll make you understand it a little bit better. Now that's just ordered pairs, where they're, right, it's like two element sets, except there's an ordered nature to it. But we have sets of all different orders, right? We have sets of all different cardinality. And so we want an ordered structure to go along with those as well. So an ordered n-tuple is a ordered set of n elements. So up here with the Cartesian plane, we were really looking at the Cartesian product of the real numbers cross the real numbers. That's this whole Cartesian plane is r cross r. We could, if we want, and a lot of people like to do this, especially in physics and engineering and things like this, we could consider the set R cross R cross R. And this would be the set of all ordered triples A, B, and C, such that A, B, and C are in R. So now it's not too much different from ordered pairs, just we can have more elements in them, and the order still matters. So an element of R cross R might be the point 1, 0, 1 would be an element of R cross R. And actually, when we do this, when you take a Cartesian product with itself many times, we just notate that like we do exponents, right? We're really kind of latching off to the time symbol here. So R3 would be R cross R cross R. That's the same thing as this up here. And so that's really all an ordered n tuple is just an ordered set of n elements. All right, let's go through an example of a Cartesian product so that we can verify that we're understanding it. This first one, we have A equal to the set 0, 1, and 2, and B equal to the set containing A and B. We want to find A cross B, B cross A, and the cardinality of each one of those. So with finite sets like this, it's easy enough to just list the elements. So A cross B would be the set of ordered pairs where the first element comes from A and the second element comes from B. And so this would be, I'll start with the element 0, 0A. There's one ordered pair where 0 is in A and A is in B. We could have the ordered pair 0, B. And we could have the ordered pair 1A. I think you're getting it now. 1B. 2A. And 2B. And so there's the set of ordered pairs where the first coordinate comes from A and the second coordinate comes from B. B cross A, on the other hand, would be the set of ordered pairs where the first element comes from B and the second element comes from A. This would be the set A0, A1, A2, B1, oh, sorry, B0, I missed 0, B0, B1, and B2. Right, so remember that the ordered pairs themselves, you can't change the order of them and get the same thing. But the set itself, I could order the individual pairs. I could list these however I want, but the ordered pairs themselves have to stay the same. That no matter how I list B cross A, I should see the same ordered pairs in it, and that should respect the order. Another thing to notice here is that A cross B is not the same thing as B cross A. Right? They're not even subsets of each other. They just have totally different elements. The element 0A, that ordered pair, does not show up in B cross A. Right? You don't see a 0A anywhere. And A0 is not the same thing as 0A. So here is another non-commutative operation on sets. We're starting to get a lot of non-commutative operations. And then for each one of these, we can find the cardinality, A cross B. We can count up the elements after listing them. There are 6 of them. And then B cross A, well, there's also 6 of them. Totally different 6 elements, but nevertheless, there's 6 of them. in the activity on the next slide, you're going to come up with a formula for A cross B in general for the cardinality of that. All right, here's one more example of, and now we'll do more than just a Cartesian product of two sets. We'll do a Cartesian product of three sets. This time, all three sets are going to be the set 0, 1. So A cross B cross C here is the same thing as 0, 1 to the third. So power on a set means a Cartesian product with itself that many times. So this is the set 0, 1 to the third, means the set of all ordered triples where the coordinates come from the set 0, 1. And we can actually list the elements of this thing. So we want ordered triples. But I start with 0. Remember, each coordinate, since we're doing the same set with itself multiple times, each coordinate will just come from the set 0, 1. So we would have 0, 0, 0 would be an example of an ordered triple. 0, 0, 1. 0, 1, 0. 0, 1, 1. I'm going to need to do a new line at some point. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. And there are how many elements here? 1, 2, 3, 4, 5, 6, 7, 8 elements in this cross product. Now, as I was listing these out, maybe you are connecting this to something you've already seen, right? These are binary strings. We would call these another way. We'll define these in a later section. Is we'll call these the binary strings of length 3. And really, once we get to that, we'll know that that's really just talking about ordered triples of binary of elements 0 and 1. And so using this concept of cross products, we'll get a lot of legwork out of that throughout the course of the semester. In this slide, we're going to do an activity. So I'm going to have you do an activity at this point. And what I want you to do is, given two arbitrary sets, find a formula for the cardinality of A cross B in terms of the cardinality of A and the cardinality of B. First, you should convince yourself that it doesn't matter what the elements of the sets are, since we're just talking about the cardinality of them. That the elements themselves won't change the cardinality, just the number of elements in it. And so make sure you try and work through these problems before moving on to the next part. Last thing I want to talk about, and this is the subject of section 2.4, are partitions. So I'll start with an example, and we'll use that to motivate the definition. So sometimes this notation is used for positive or negative integers or real numbers or rational numbers. So putting a little plus in the superscript indicates that we should just consider positive ones. So R plus would be the set of all real numbers that are bigger than 0, so just the positive real numbers. And R minus would be the negative real numbers. And we could do that with integers or rational numbers, whatever we want. Sticking a plus or minus up there just indicates positive or negative for the set. That's pretty standard notation. So we'll define those two sets and consider this set A. I used a curly A here, which is a set of sets. R plus, R minus, and the set containing 0. So this set has 3 elements. Each one is a set of real numbers. And this is actually a very special set of real numbers because it has a really nice property. So I want you to notice the following things about this set of sets. First, that each set in A is non-empty. Right? R plus certainly has some things in it, right? Like 3 is in R plus, so it's non-empty. Same with R minus. I don't know, negative 1,000,000 is in R minus. So it's definitely not empty. And then the set containing 0, well, that has cardinality 1. It's not empty. So each one of these is non-empty. That's a good start. And then each pair of sets in A is disjoint. Remember that disjoint means that their intersection is empty. They have no elements in common. And so no matter what pair of elements you look at here, like R plus and R minus, if I take the intersection of those two, well, ask yourselves, are there any common elements? Are there any real numbers that are both positive and negative? And the answer is no. And so this intersection would be the empty set. And you can do that with any pair, right? R minus doesn't contain 0. So if I take the intersection of R minus and the set containing 0, I also get the empty set. That's just 2 pairs here. There's 3 pairs total. R plus and 0, same sort of thing would work out there. We'd get an empty intersection. And so we'd say each pair of sets here is disjoint. And the term there is the whole collection is pairwise disjoint. That's what it means when you have a collection of sets and each pair of sets is disjoint. We call that pairwise disjoint. And then the last thing, so that's 1 and 2, the last thing I want you to notice is that the union of the sets in A is all of the real numbers. So we could actually, I'll actually depict that using a the real number line. So this is another way I can depict certain really big sets. Here's the real number line. I'll put 0 right there, 1, 2, 3, 4, and so on. -1, -2, -3, -4, and so on. And so R plus is this set, so I'll draw I'm having a little trouble when it gets fine like that. So I'll draw an open circle because we're not including 0 there. So that's R plus is that part of the real line. In blue, I will put R minus. So again, that's an open circle around 0 because it doesn't include 0, and then everything to the left of 0. So that's R minus. And then right at 0, we have the set just containing 0, just a single point, and so I'll put I'll use green for this. And right there, we've included the set 0. So every single element of the real numbers is in one of these sets, R plus, R minus, or the set containing 0. Right? That's the same thing as saying every real number is either positive, negative, or 0. And so this is a special property of a collection of sets. When this happens, we call the collection of sets a partition of the set of which they're subsets. So A here, curly A, is a partition of the real numbers of R. It's certainly not the only partition of the real numbers. There are many other ways we could break the real numbers up. But nevertheless, when we have a situation like this, where we have a set broken up into subsets such that each one is non-empty, they're pairwise disjoint, and their union is the real numbers, or their union is the entire set, then we call that a partition. And when you have these 3 things, this is why this is so special, is that now we can say every element of the real numbers belongs to exactly one set in A. Right? Pick any real number you want, say 1,000,000. That's an R plus and not an R minus and not in the set containing 0. It's in exactly one of them, no matter what real number you pick. If I pick pi, that's an R plus, not R minus, and not the set containing 0. And so this is a very special property. We'll get some use out of this later. Partitions are pretty special because we'll get to that later. They're special. They're neat. So let's take a look at an example of partitions in order to make sure we're understanding them. So for this one, we're going to list all of the partitions of the set containing A, B, and C. So I'm going to label these. Whoa, that's not what I wanted. I'm going to label these script A1, script A2, and so on. So script A1. Well, let's just give a partition of the set ABC. So remember, every partition is a set of sets, and maybe we could break up this set into just the one element subsets. And for any partition we list, we should make sure that it really is a partition, right? We should make sure that each set is non-empty inside of it. Yep, those all contain one element. None of them are non-empty. That they're pairwise, that the set itself is pairwise disjoint. Yep, no two sets have contain the same element. And lastly, that the union of the three sets is the original set ABC. And it is, right? We have all of them in there. All right, let's try for another one. Script A2. Well, let's see. How else can I break this set up into non-empty pairwise disjoint subsets? Well, they have to have something in it, so maybe I'll just put the set A there. And then I already listed the one with B and C as different sets, but what if I put those together into a set? Set A and the set B, C. That's a partition as well. It satisfies all three properties. A3, maybe you can see where I'm going with this now. A3, why don't I stick A and B together and then put C by itself? Yeah, that will work. And right, so going off of that theme there, what if I stick A and C together and leave B by itself? So in the first one, each set had one element in it. In the second one, it was one element set and one two element set, and that's the same for all those last three, a one element set and a two element set. And that's all of them doing that. But there's one more partition here, and this is sometimes called the trivial partition. And that's just the set itself. Now you might think that's weird to just have the set itself being a partition, and really not much is being accomplished by this. But it is a partition. So we'll go through all three conditions to make sure it really is. So first, yeah, the set ABC is non-empty. So we have that satisfied. It's pairwise disjoint. Really, it can't share any elements with any other set because there's only one set here. So that's satisfied. And lastly, the union of all the sets in it is the set itself. Well, there's only one set, so yep, that's the set itself. And so this works. Every element of ABC belongs to exactly one element of that partition. I'll take a second to just remind you what the cardinality of a partition is. So remember, the cardinality of the original set is 3. The cardinality of a partition is how many sets you've divided the original set into. Right? It's the same thing as the cardinality of any set. It's just now our sets contain other sets. So the cardinality here of the partition A1 would be 3, since I divided it up into 3 sets. Cardinality of the set A2 would be 2, since I divided it up into 2, and that's the same for, oops. Sometimes my hand doesn't do what I want it to do. A3 also has 2 elements. A4 also has 2 elements, and lastly, A5 has 1 element in it. And so that's the deal with partitions. This can get a little bit confusing, right? That the cardinality of a partition is the number of sets, because the sets themselves have cardinalities, right? A1 I could describe as a partition where each part of the partition has 1 element in it. Of course, the partition itself has 3 elements, each one of those sets. All right.